This video is the second half of an explanation of the shell program. The first video was titled Shell Program Explained, and in that video I walked through the code of a simple shell program from the XV6 operating system, which is an educational kernel from MIT. I gave an overview of and outline of the structure of a shell program. In this video, I'm going to continue and walk through the code that parses the command line and builds a tree representation of the command line. So the first function that I want to look at is the GetToken function. And in order to understand that, we need to look at what that function does. There's a buffer, a fixed size buffer, containing the input line. So we assume that that has been read in. GetToken takes 4 arguments and returns a result. Here is the function prototype for GetToken, and we can see it takes a pointer to a pointer, a pointer to a pointer, and a pointer to a pointer, and it returns an integer. So what's going on here? GetToken is going to scan the buffer characters and find the next token. The arguments are PS, ES, Q, and EQ. PS is a pointer to a variable which presumably is already set to point to where to begin the scan in the buffer. ES is the end of the scan, and it points to the character or the byte just after the last byte we want to consider in the scan. The result of this will update this variable here. We can call it S, so PS stands for pointer to S. We'll update S to the next character that we want to start the next GetToken call on. Q and EQ will be set to point to where the token is found. So here we're going to scan this input and we're going to find the first token. Here's some white space, and presumably the token starts here. So we will set Q to point to where the token begins, and we will set EQ to point to the byte after the token. And as a result of calling GetToken, we'll update S to point to the thing after that where we want to start the next scan. Actually, we'll skip past this white space that follows the token and end up altering S to point to the first non-white space character. So after GetToken is called, we will set things this way. Q and EQ may in fact be null, in which case we won't update them. But if they are not null, then GetToken will update them to point to where the token is found. GetToken also returns an integer, and the integer tells what sort of token was found. So we can parse operator tokens like the vertical bar for piping, semicolon, ampersand, or parentheses, or the symbols for redirection. Most of these tokens are single characters, but the output redirection here is 2 greater than symbols. For each of these, the GetToken function will return exactly the character. In the case of the greater than, we will return a plus character. For anything else, we're going to return the letter A. So for file names and command line options and so on, we return just the letter A to indicate that it's not one of the operator symbols. And for anything else, basically, if there is no token, we will return a 0, or you can think of it as a null byte. So if there is no token before we reach the end of the scan period, then we return 0. Okay, now let's take a look at the code for GetToken more closely. We've got a couple of constants here. White space is defined as a blank tab, return, new line, or the vertical tab. And we have the symbols here that are tokens, so we can scan for those. Okay, let's look at the header. We can see the arguments, PS, ES, Q, and EQ. So what we're going to do is start with S, and then at the very end of this function, we're going to set PS, we're going to update it to point to S. So during the function, we'll be working with S directly. So we have a variable S, and we are going to start by setting it to point to the first byte that we want to look at. And we'll advance S here and other places, and eventually, before we return, we will update the pointer that we're supposed to update. So what do? First, we advance S to the first non-whitespace character. So here we're checking to see whether the thing we're pointing at is one of these whitespace characters. We make sure that we're not at the end yet, and if so, we just keep incrementing until we either hit the end or we hit something that's not whitespace. If our argument Q is not null, then we need to update it. So we set that to point to where the token begins. And we also collect our return value. So we've got a variable here which will be the character that we will end up returning at the end of this function. Here's the end of the function, and after we update PS, we return that character. So if we're pointing to a single character, such as less than or vertical bar or one of the others, then right here we're setting the return value to that single character. Then we have a switch statement that looks at what exactly we are pointing at. That is, it looks at the first character of the token. And we have several cases here, which I'll go through next. Here's the end of the switch statement here. So it's pretty short and sweet. If we're pointing at the null byte, we immediately break. That's what we found. We're pointing at the null byte. There was no token. So in that case, we need to return a 0. That is, we return the null byte itself. Otherwise, if we're pointing to vertical bar or one of the parentheses or semicolon, ampersand, or less than, then we've just got a single character token. And we can increment S to point to the character directly after the token and break. So we're done there. If we're pointing at a greater than symbol, then it's possible we have 1 or 2 greater than symbols. So if it's just 1, we advance the pointer to the next thing, and then we break. But if the character after that is also a greater than symbol, then we're going to be returning a plus sign. Remember that if the token is 2 greater than signs, we return a plus sign. So that happens here, and we advance the pointer a second time to point to the character after the second greater than symbol. Finally, if it's none of those things, then it must be something else. And in all other cases, such as the file name or some kind of an option that was on the command line, we will set the return code to A. And then we scan here. What we're scanning for is the end of the token. So we look for something that is a white space. Okay, so we keep scanning. If it is a white space, we keep if it's not a white space, we keep scanning. If we hit a white space, we stop scanning. We also watch out for some other symbols. So remember, our symbols are the various punctuation symbols we might encounter. So if we hit one of those, then we also stop the scan. And lastly, if we advance S to the end of the string, to the null character, we stop the scan. But if it's not the null character and it's not a white space and it's not one of our symbols, then we advance S until we hit something that stops us. Finally, and here's where we continue, if our last parameter, EQ, is not null, then we update it. So here's our last parameter, EQ, and if we actually are pointing to something, then we update it to whatever S points to at that point. That will be the character directly after the token. Finally, we have another loop where we scan any white space. So if S is pointed at white space, we loop. So while s is one of the white space, or pointing to one of the white space characters, we increment s. If we advance s to be equal to the end of the string, if we advance s to be pointing to the place we should stop, then we stop. So that advances us to either the null character at the end of the string or to something that's not white space. And then we update PS. So PS is pointing to some variable s, and here's where we store the new pointer in that variable. The next time we call GetToken, we will begin the scan at that new place. Next, let's look at the peek function. Peek is going to look past any whitespace characters and find the next non-whitespace character. So here's an example where we're calling peek. And peek is a Boolean. It returns an integer. So PS is where we start the scan, ES is where we end the scan, and in this particular use of peek, we're looking for characters vertical bar, closing parenthesis, ampersand, semicolon. Peek works a little bit like GetToken. PS points to a variable that contains a pointer to where to start the scan, and ES contains a pointer to the character after the last character where we stop, to the null character. So peek starts by using a local variable s rather than using double indirection. It copies the pointer to the starting position into the local variable s, and then when it's done, it copies the local variable back. In this loop here, we scan past any white space. So as long as what we're looking at, what we're pointed to, is within the white space set, is a white space character, and we are not yet at the end, that is, s is less than the pointer to the null character, then we keep advancing s. So after that loop, we're pointing at something that is either the null character or something that's not white space. And we update the pointer, and then we return our Boolean. We ask, is it not the null character? The null character is 0, that's equivalent to false. And is it one of the characters in the set of tokens that we were scanning for? If it's one of the characters in this set of tokens, the set of characters, then we return true. Now let's take a look at the parse command function. The parse command function has passed a pointer to the buffer, the input buffer that contains the characters we need to scan, and it returns a pointer to the tree that it builds as a result of that. First of all, it figures out where the null character is. So string length searches a string for the null character, and this statement right here sets ES to point to the null character. Then it calls Parseline to do the work, passing it a pointer to the variable s and a pointer to the end of the string. Then it checks to make sure there's nothing left and calls null terminate. So peek is used here, and the set of characters we're providing is the empty string here. So peek will just basically advance past the any white space and hopefully come to rest at the null character at the end of the string. So we check that. If s is not equal to es, then we've stopped on something besides the null byte at the end of the string, and so we print an error message here, and we then invoke panic, which will abort the process. But assuming everything's okay, there's nothing beyond whatever Parseline consumed, then we call null terminate, and null terminate is going to walk the tree and, as we discussed in the previous video, replace all of the characters after the program names and file names and command line options with a null byte, so that those will be null terminated strings. Next, I want to take a look at the functions that do the recursive descent parsing. There are 5 functions: parse exec, parse redirects, parse pipe, Parseline, and ParseBlock. Here I'm showing essentially the context-free grammar that will be accepted by the shell program. So we have the different kinds of nodes that will be created, but here we're showing them as grammar non-terminal symbols. So let's take a look at block, for example, since it's the simplest. What this function, ParseBlock, will do is read in a left parenthesis, and then it will recursively call the function that parses a line. That's right here. And let's not worry about what a line is, but after that has been parsed, it will then parse a right parenthesis or scan a right parenthesis, and then it will call the function that parses the redirections, which is parse redirects. So next I want to take a look at pipe. Pipe will call parse exec up here to parse some stuff, and then it will possibly parse a vertical bar and then call parse pipe recursively. That is, it'll call itself to do some more. I'm using the square brackets here to indicate something that's optional. So if there is no vertical bar, parse pipe will not call itself recursively. A line will be parsed by calling parse pipe first, and then we parse 0 or more ampersand characters. The braces used here is a standard notation for indicating 0 or more. And then we optionally parse a line. If there's a semicolon there, we pick it up and call parse line. That is, we call ourselves recursively. So I'm not sure why there's 0 or more ampersands here. It seems like to me it ought to be just either 1 ampersand or none. But in any case, that's the grammar that this thing parses. A redirection is either a less than, a greater than, or 2 greater than symbols, followed by something. And this will be the file name, of course. So we can have 0 or more of these. And finally, we get to the meat of things, which is the exec node. So an exec is normally a sequence of tokens. The first one will be the program name, and any additional tokens will be the options. This notation, a brace with a plus sign, means 1 or more. So we have to have at least the program name, and we may have 0 or more options following that. Now we also see redirects here. Okay, so we can have a less than or greater than sign and a file name following that. In fact, we can have it in any place. We can even have the redirections before the program name. It turns out this is something my shell will do. I didn't even know that I could put the redirections before the program name. It's probably not something people normally do. But in any case, that's the grammar that we have here. So before and between any options, and we can have 0 or more redirections. And finally, we see an open parenthesis or block. This is a choice. When we're calling parse exec, it will either go this way or it will go this way. Here we use the peek function to look and see whether we've got a left parenthesis. We don't actually scan it at this point. We then call block, and in block, that left parenthesis is actually scanned. So I haven't really drawn this quite as a context-free grammar, but I wanted to give you the idea that it checks for a left parenthesis. If so, it calls block and is done. Otherwise, it goes and does the stuff that's on this line, the sequence of tokens that indicate the program name and the options. So now let's take a look at this pipe here in more detail. And we see it parses an exec, it calls parse exec, and then if there's a vertical bar, it calls itself recursively. Now, maybe you remember this from your compiler class. Here I've drawn the rule in a more standard context-free notation, and we see that there is a right recursive rule here. Pipe goes to exec, bar, and then pipe again. And when we have a right recursive rule like this, it corresponds to a right recursion, building a right recursive tree with a right chain down here, and it also corresponds to right associativity. So if I have something like something vertical bar, something vertical bar, something vertical bar, something, without the parentheses, this thing will parse that, assuming each one of these A, B, C, and D items is an exec, then it will parse it and it will build a tree and it will call itself recursively. So basically the first invocation, if you will, of parse pipe will pick up the exec, the vertical bar, and then it will call itself recursively and build a subtree. And that subtree will then pick up the B, see that there's another pipe, call itself recursively. The third invocation of parse pipe will do the same thing. And finally, the last invocation will pick up the D, see that there is no vertical bar, and then it will just essentially use this rule. And the result of all this is we get a tree with right recursion. And what that corresponds to is grouping like this, like we've shown. I've added parentheses here to show how this particular expression will be interpreted with our parser. Okay, now let's focus on the pipe rule, and we'll look at the code for parse pipe. We call parse exec, and then we check to see whether there's a vertical bar, and then we call ourselves recursively. And the goal of each one of these functions is to build a tree representing what has been parsed. So when we look at the code for parse pipe, we'll see how this is done. So here we have it, and we see that it returns a pointer to a tree, good, and we see it takes two arguments, PS and ES. These are our familiar pointers that tell us where in the input buffer we should be looking for, in this case, an example of this pipe construct with exec and the vertical bar and so on. PS is a pointer to a pointer. More precisely, it points to a global variable, which we can call S, and that global variable tells where in the buffer to start the scan. We will update that global pointer, so that's why we have a pointer to it. And ES is simply a pointer to the end of the string, or more precisely to the null byte after the part we want to look at. So here we see the call to parse exec, checking to see whether we have the vertical bar, and a call to parse pipe. And so we're first picking up an exec unconditionally, and that builds a tree. We assume that each one of these parse functions will build a tree and return it. So when we call parse exec, it builds a tree, and we save a pointer to it in command. Then we use our peek function, and it returns a Boolean. It returns true if the next thing we're looking at happens to be a vertical bar. And if that's the case, well, we scan it. So here we are scanning it. The Q and EQ parameters to GetToken will be set to where the token is if they're not null, but we don't really care about where the vertical bar is located. We just care that it exists at the next position. So we're passing in null pointers here. And then we will call parse pipe, again with PS and ES. So we call ourselves recursively, and this builds some kind of a tree and returns it. This is one of the constructor functions. This is the pipe command, and it's passed a pointer to the left subtree and a pointer to the right subtree. Whatever the exec returned will be used as our left subtree, and then whatever the recursive call returns will be used as the right subtree. We create a new pipe node, and that's what we've got now, and we return that. Next, let's take a look at Parseline, because I think it's the next most simple one. It calls parse pipe, and then checks for ampersand, and checks for a semicolon, and optionally calls Parseline. So here's the code for that. We see, again, that it's passed a pointer to the global variable S, which tells where in the input the current scan position is, as well as a pointer to the end of the string. And we see it calling parse pipe right off the bat, and that returns a tree, which we save in command. Then we check to see whether the next thing is an ampersand, and if it is, we pick it up. And this is in a while loop, so we pick up a number of ampersands, 0 or more. And for each one we pick up, we take the tree that we had from before and we add a new root node. In other words, we allocate a background node using the previous tree as the subtree, and that then becomes our tree. So command is redirected to point to the new node that we allocated. And I'm not sure, as I said, why it's 0 or more ampersands. The only thing I can think of is that perhaps in testing the kernel, they wanted to be able to create a number of processes conveniently all at once. And by typing a program name followed by, let's say, 5 ampersands, what this is going to do is create a tree with 5 background nodes, and each one of those will be creating a subprocess. So each one of those will be causing a fork, and so you'll end up with a number of different processes running. But in any case, we pick up the ampersand or multiple ampersands if there happen to be more than one. And if there are none, then we don't modify the tree. We just have what pipe called without the background node attached at the root. And then we take a peek at the next token. So remember that peek will advance past the white space and ask whether the next token is one of the characters provided in the string here. So if the next token happens to be a semicolon, then we scan it. Again, the third and fourth parameters to GetToken are set to null. They could point to variables to update so that we could remember where in the input string that token occurred, but we don't care any longer where it occurred. Then we call Parseline, again updating the pointer to where we are in the scan. That returns a subtree, and then we build a list node. This is a constructor function that will allocate the list node and fill in the left and the right fields with the pointer to the left subtree, which is the program on the left of the semicolon, and whatever we found to the right of the semicolon. And finally, we return that. Next, let's take a look at ParseBlock. And you can see that it picks up a left parenthesis, calls Parseline, picks up a right parenthesis, and then picks up any redirections that we may have. So here's the code for ParseBlock. Again, passed a pointer to where to start the scan and where to end the scan, and it returns a pointer to the tree that it builds. First thing it does is it checks to make sure that the next thing is a left parenthesis. Remember I said that for exec we check to make sure that we have a left parenthesis, and if we do, we call ParseBlock. This is the only place we invoke ParseBlock, and so we know for sure that we will have a left parenthesis at this point. So that's why we're just doing a quick error check to make sure that that is in fact what we expect. So we've got the left parenthesis. Then here we call GetToken to scan past the left parenthesis. And here we call Parseline to pick up a line, and that returns a pointer to the tree that it constructs. Then we make sure that we have a right parenthesis. If we don't, we have an error message, and we print that there's a syntax error, and this will abort the process. Assuming we have the right parenthesis, then we scan it with this call to GetToken. And then finally, we have the call to parse the redirections. And now this is something slightly different, because here we're passing not just PS and ES, but we're also passing a pointer to the tree that we've built up so far. Okay? And this will possibly add a new root and in any case return a pointer to the resulting tree. So remember that the redirect construct is a less than followed by a file name or greater than followed by file name, or greater followed by file name. And we can have 0 or more occurrences of this. So let's take a look at how that works. And here's the function that parses the redirections. It returns a pointer to the tree that it constructs. But as you can see, it takes a pointer to the thing that this is applied to. The redirections are applied to something. In the case of the exec, it's applied to a node that is the program. So we'll see that in a second. And for this down here, the redirections are applied to whatever occurs within these parentheses. So all the stuff that occurs within these parentheses. It could be pipes or sequencing, whatever. But the redirection happens before any of that is executed. So here we have a pointer to the subtree that we're going to use, and we're going to be adding a root and replacing it. So we've got a while loop here. So we are checking to see whether the next character, peek, scans past the white space and looks at the next character. If it's a less than or greater than, then it's one of our three things, either less than, or greater than. But it just asks, what is the next character? And if it's one of these two, then we know we have one of those three options. So whatever it is, we call GetToken and save what GetToken returns. If it's a less than, this saves a less than character. If it's a single greater than, it saves a greater than character. If it's two greater thans in a row, it saves a plus in token. And so then we're going to be switching on whatever we had here. But before we do that, it needs to be followed by a file name. So I'm showing that here. So whichever we had, we've got to have a file name. So at this point here, GetToken is invoked. And now we are passing it a Q and an EQ. These are local variables. They will be updated. We're actually passing, not Q, I should say, but we're passing the address of variable Q, and we're passing the address of variable EQ. Q and EQ are pointers to the first byte of the file name, in the case of Q, and to the thing just after, to the byte just after the file name, in the case of EQ. So we call GetToken, save where we found the file name, and if it was a file name and not, say, for example, some other punctuation character, then GetToken will return an A. So we check to make sure that we've actually got a file name or something that looks like a file name. And if not, we have our error message. Then, finally, we switch on whatever kind of token we had, less than, greater than, or two greater than symbols. And we call redirect command, which will allocate a redirect node and fill it in. The redirect node has several fields. It's got a pointer to the subtree, that's the first argument. And then it's got a pointer to the file name and a pointer to where the file name ends, or more precisely to the byte directly after the file name. Later, we'll have to go through the tree and overwrite that byte, whatever it might be, with a null byte, so that after that point, Q will point to a null terminated string. So we pass in EQ, and if it's a less than, the file descriptor, which is the last argument, will be a 0. If it's greater than or greater, then we're updating standard out. 0 corresponds to standard in, 1 corresponds to standard out. So these are the files that we're going to be closing and reopening when we execute this thing. And finally, the argument here is the mode word. And so this is a sequence of bits. In the case of a redirection with a less than, we're going to be opening the file read-only. In the case of this, a single greater than symbol, we'll be opening the file name for writing only. If it doesn't exist, we want to create it. If it does exist, we want to truncate it to 0 length, so we overwrite it. With two greater than symbols, we leave out the truncation. So this is for appending to the output file. This is for creating a new output file or overwriting the one if it exists. This is for appending to it. if it already exists. Finally, let's take a look at the parseExec function, which allocates an exec node. Remember the syntax. It can either be the first or the second thing here. It could be a sequence of tokens, possibly with redirections interspersed, or it can be an open parenthesis followed by a block. It's easiest to dispense with the second case first. So here we're looking at the code of parseExec. It's passed a pointer to the variable s, which is the starting scan position, and es, and it returns a pointer to a tree. All right, first we check to see whether the next non-whitespace character in the input is a left parenthesis, and if so, we call ParseBlock and return. So that handles that case pretty easily. But now we have to look at the first case. So let's take a quick look at what we might encounter. Typically when you type a program in, you type it in as I'm showing first here. You write the program name, and if you have options, you supply those. And then finally you would have a redirection, and typically they would come after the options. But it turns out with this syntax, you can put the redirections anywhere, even before the program name itself, or interspersed with the options. So we'll look at this as an example input here, but either of these would be handled in the same way and would create the same tree. So let's go back to the code and just look at the parsing aspect of it before we look at how the tree is built. So we have a while loop here. What we're doing first is we're calling parse redirects. So we're doing this right here. And then in this while loop, we are checking to see whether we've got something that's not a punctuation character here. Something that's not a punctuation. And we know that the next thing is not less than greater than symbol. Otherwise, we would have kept picking it up in the redirections. So we know it's not that. So here we're checking to see whether it's one of the remaining symbols. Okay? Vertical bar, closing parenthesis, ampersand, semicolon. And as long as it's not one of those, it is presumably a file name or an option. Okay, so if it's not one of those, we keep looping. So we check to see whether it might be the end of the string here, and if so, well, we've reached the end of the string and we're done, so we break out of that. And here's the while loop. But assuming it's not the end of the string, we make sure that we've got a file name or option, something that looks like a file name or option, or more precisely, doesn't look like punctuation, or the end of string null character. If it's a problem, we can print a syntax error message here. And then we call parse redirections again and loop back until finally we see something that is one of these symbols or the end of string symbol. Okay, now let's take a look at how we're going to build the representation of this thing. So here I'm showing the exec node that we're going to be creating. We've got a local variable called return, and that points to the tree that we've built so far. So here we're calling the constructor function, and this allocates the node. It doesn't fill it in yet, okay? It basically just allocates a blank node with the type code set with our two fixed size arrays of pointers here, but they're not yet filled in. Okay, so now we've got this set up here. And command is a pointer to this exec node. And then we're going to call parse redirections here. And we're going to pass it the tree that we've built so far. Well, the tree that we've built so far is just this exec node that it hasn't even been filled in. But remember what parse redirects does. It's passed a tree, and it will allocate a redirection node. So it allocates a redirection node here. And it's got a pointer to where in the string, it points to the file name, not to the less than symbol. And it's got a pointer to where it ends, so the byte directly after that. And it's got the mode and the file descriptor. In this case, it's an input, so that would be 0. The file would be open for read-only. And finally, it's got a pointer to the subtree. Okay? And we see in our code that we're passing it in the tree that we built so far and updating it. So now return points no longer to that, it points to that. Okay, so we've already built the redirection here that will apply to this We've already built the redirection here that will apply to this exec node once we find the program and the options. So then we continue with this, and at this point we find that we don't have a punctuation symbol, otherwise we would have exited, and we're not at the end of the string, so therefore we must have something that looks like a file name or option. And we are going to fill in these argv pointers and the e-argv pointers. So here is where we're scanning the file name or the option. We have local variables q and eq, and we're passing the addresses of those variables here, so they will get updated to point to where the first program name is. So q would point there, and eq would point, I'll do it this way, eq would point there. And then we come down here, and we see we've also got local variables, a local variable argc, and that's going to be our index into this array. Okay, we'll start it at 0. So argc is pointing to the first element, the 0 element. And at this point, what we do is we fill in a pointer to where the file name begins and to where the file name ends. So at this point, here's the first element of these arrays. And we will fill it in. We'll copy q. So q points there, and eq points here like that. Okay, so now we have that filled in. And then we check to see whether we have overflowed the array. We start with 0. We have 10 elements. So after we fill in element 9, we increment that, and that argc then becomes 10, and we find out that that's the size of the array 10. Oops, we filled in the last element. We don't have room for the null that we have to add after them. So at that point, we have too many arguments. We print an error message. But otherwise, what do? Well, in our syntax, we need to call redirection after each one of these file names and options. So we call redirections. There's nothing going on here. We don't find a less than or greater than symbol. So that parse redirects will not do anything. Okay, let me go back to the code for parse redirects. Here's the code for parse redirects. It's passed in a pointer to the tree that's going to be modified or that we're going to add a root to, and it does this while loop. And you can see that if the while loop doesn't see a less than or greater than symbol, it merely returns whatever it was passed. So here, this call right here does not change our pointer. We're still pointing at this redirect node here. So then we loop back, and just to walk through this thing a second time, again, we see that what we're looking at is not one of the punctuation characters. We're not at the end of the string yet. We are, in fact, looking at something that looks like a file name or option. So we've already incremented argc, so now we just, when we called GetToken, we updated q and eq to point to this first option. So now at this point here, we're going to fill in those pointers in the argv and the eargv. So at this point, argc is pointing to is 1, and we just fill in pointers here and here. Okay, my diagram's getting a little bit messy here, but I think you get the idea. And then we do redirections again. We see that at this point in the down here that we do in fact do something in this call to parse redirects. Parse redirects at this point is passed a pointer to some tree, which I can show symbolically here like this, some tree, I don't know, some tree. And what parse redirects is going to do is going to take that tree, add a root, and then return a pointer to the root. So when we call parse redirects here, what we'll do, and I'm not sure if I have enough room to add this here, but we'll add a new redirection here. This is another redirect, a node, and we'll make it point to this, and then we will update return, or the return variable, to point to that. So now we have 2 redirection nodes pointing to the exec. Later, when it comes time to execute this tree, we'll do this redirection first. We'll do the second redirection first, and then we'll do the first redirection down here, and then we will execute the program. Just to finish up here, after we exit this loop, we plug in the null values, and then we return that tree. So we'll plug in the pointers for the final option here, like that, and then finally we'll plug in a null pointer at the end, and that's exactly what we want. Oh, that is the tree that we want. In explaining the code just now, I realize I've made a mistake. This while loop here calls GetToken to pick up the file name or option right here, and it will call it 0 or more times. In the grammar that I presented here for the exec node, I said that there has to be 1 or more tokens here because I just assumed there has to be a program. But in fact, this grammar will parse 0 or more occurrences here. So I used plus, braces with plus to indicate 1 or more. I really want 0 or more, so I'll eliminate that. Sometimes you see brace with a star for 0 or more, so maybe I should replace this with a star. But in any case, this while loop can very well parse 0 file names or options. If that happens, then the exec node will be filled in with nothing right here. In other words, the 0, the null, will be placed in the first position. We won't have any of that stuff going on. And if we go back to the run command, which I discussed in the other video, in the first video in this series, here's the run command again. And recall that what the run command does is it basically has a big switch statement, looks at what kind of node it is, and then executes it. For example, if it's a redirection node, it closes whichever standard input or standard output is required to be closed, and then it replaces it by opening the file. Now, here's what it does for the exec, and we see that there's a check right here, and it asks, is the 0 position null? In other words, is there at least one thing there? And if there's not, it exits immediately. So that's why that if statement is there, because the user may type in a line with nothing on it. And so that would be this case right here, in which case it just terminates immediately. Finally, we need to describe the null terminate function. Remember that in the overall function, which is parse command, we call Parseline, and that builds and returns a pointer to the tree. And then after that, we invoke this null terminate function. We need to go through the tree after it has been built and after we're done with the parsing, and we need to add or replace the byte directly after file names and command line options with the null byte. So we need to update the argv pointers in the exec nodes, and also for a redirect node we need to add the terminating null byte after the file name. So let's take a look at the code that does that. It's pretty straightforward. It's a function that is passed a tree and returns the same tree. It just modifies the tree, and it recursively walks the tree. So it takes a look at the type of the root here, and then it does a big case statement on that, and calls itself recursively, as you see here and here, and then finally returns. So for example, the pipe node is dealt with by just calling itself recursively on the left subtree, calling itself recursively on the right subtree. Likewise, list is just a couple of recursive calls, and the node that executes functions in the background just has a single subtree, and so we recurse on that. Finally, let's take a look at what happens when we encounter an exec node. Well, we just go through the argv array in order, and we follow the pointer, okay? And wherever it points, we write the null byte there, okay? argv is a pointer to characters, so we just are writing a single byte, and that will be updating these bytes that follow the program name and command line arguments. Likewise, for the redirect node, we only need to update the e-file field, or I should say we need to update the byte that the e-file field points to. So that's what we do right here. We call ourselves recursively, but at the same time we update that byte with this line here. Before I wrap up, I want to mention that I'm thinking about making a video series on the xv6 kernel. That's quite a big undertaking, and I'm not sure whether I'll be able to complete it. So if you want to encourage me, please leave some comments on this video. And you might want to click the appropriate YouTube buttons to get notified if I actually complete this series. In any case, we've done a pretty thorough walkthrough of the code for a simple shell, and that's it. Thanks for watching.